So once you see the job status changing to running, you can always, again, click in Open Session, and this will connect to your session. So once you arrive in your Jupyter Notebook session, you should be able to see something that looks like this. This is a very typical Jupyter Lab web page. So you have a bunch of different informations that you can play around and try to explore. There's different things that you can do here, from changing your Python kernel to restarting your kernel, interrupting jobs. There's several different things that you can do here, so it's very worth to explore. Also here on the left, you're gonna see several tabs which will allow you to create folders. This session is going to be run inside Frontera, so everything that you have in Frontera, from your Scratch folders, your work folders, everything is going to be accessible from here. And you can always create folders, new folders, upload files, and also download files if you need. So you also be greeted, once you open this page, you will be greeted with this installation notebook, which is just a very generic setup procedure where you're going to be downloading Quantum Espresso and also compiling Quantum Espresso, and also downloading the Jupyter notebooks, and also installing EPWPy, which is we're going to be using to run all of these notebooks. So it's very straightforward. You can follow all these steps one by one. Here there's some Python lines that will basically go into your work directory. This will download Quantum Espresso. It will configure and compile it for you, and also will create a small Python file called pathQE, which will store the path of your Quantum Espresso installation, and the notebooks will use these installations to run everything else. So this will do everything at once. This second set of lines will essentially copy all the notebooks that we're going to be using in this tutorial, and also many more, for like examples on how to use EPW and Berkeley HW. And finally, step 3 is basically the installation of every Python library that we're going to be using, and we're going to need for both NumPy, Matplotlib, but also for the EPWPy library itself, which we will be downloading from TestPip at the moment. This will be always updated in the future. If anything in this process change, any of these lines change, this will be updated whenever you are accessing it. And if you have any kind of problems, any kind of troubles in the installations of using any of these notebooks, again, you can always reach any of us, Sabia, me, or also Feliciano. So once you set up everything, you should be able to see this folder called Notebooks Basics. And this folder, it should contain all the notebooks and examples that we will have at the moment. We will always be updating this, so we might have like different examples in the future, or maybe extra ones, but they are all here, including the installation notebook that we just talked about. So we can actually pass through some of these notebooks to see more or less how the structure of these Jupyter notebooks work. So if you double click any of them, you should be able to see a page that looks sort of like this. So this is essentially let's say a combination of LaTeX and also Python. So you have some LaTeX lines here that you can always click on the play button on the top to compile, and this will compile the LaTeX. And the same thing happens with the Python lines here. So if you click play, you will be executing this cell in real time in Frontera. So this first example that I want to quickly pass by, and also to show a bit how the EPWPy structure works when you are running calculations, is related to transport calculations in real materials. So exactly one of the applications of EPW. Again, like in any type of notebook that we'll be doing here, since it's a Python structure, you always find a series of libraries that will be important. This will be the header of any of these notebooks. All of them contains a series of imports that we're going to need. Once all of these things are set up, so we can always set up some global variables that we're going to use, and also some folders that we're going to be using. All of this is very schematized here, and also explaining all this text on the top. This particular path here, you have the option of either setting manually the path to your Quantum Espresso installation if you want to use a specific one, or you can use the path Python file that was generated on the first step on the installation notebook. Both of the options will work. You can choose whatever Quantum Espresso version you want. So once you have all of these generic global things defined, the first thing that you want to do is define your material. So in this case, we're going to be studying silicon. So in Python language, this is going to be our object, because this is going to be purely object-oriented coding. So our object is basically an EPWPy object that you can see here, where you can define a series of variables that are both related to EPWPy itself, but also to either Quantum Espresso, EPW, or Berkeley GW. So all of these generic variables that you want to use throughout your calculations, you can always define here, and this will be carried on throughout the rest of the code too. We can also always print some attributes. This is just to explain how you can access the different dictionaries within the library and call, for example, which pseudopotentials you're using, the different atomic species that you are using, and so on. All of this information is always accessible from the library if you just call it. So if you execute this Python line here, clicking play, what you should be seeing is a screen that looks roughly like this. This means that the EPWPy library was correctly loaded and it's correctly executed. You see that in this case, he found a pseudopotential at the pseudodojo library, and it downloaded automatically. So this is done because of this small flag here called pseudo-auto-true. You also have the option, as on the Quantum Espresso case, you have the option to set this to false and manually set a path where your pseudopotentials will be contained. But in any case, if you don't want to worry about it, or if you want to run any type of high throughput calculation, which requires you to iteratively download several of these files, you can just set this to true, and it will download everything for you in real time. So this is basically to tell us that the Python structure was correctly created and our silicon object is fine. Once this object is defined, what we can do is proceed to the steps that we need in order to run a transport calculations in EPW. So if you are familiar with it, there's two ingredients that we need. One of them is the electronic contributions, which comes from SCF and band structure calculations. And the second one are the phonon contributions, which comes from the phonons, from the lattice vibrations. You have to compute these two things. So the first thing that we're going to do is compute the electronic part. So you can see here that we start with an SCF calculations, where we are just solving the Kohn-Sham equation that you see here. This is done simply by these lines of Python code that you see here. The structure of EPWPy for any type of calculation that you will run will always be the same. So we have 3 lines in order to run any type of calculations. So once you define your silicon object, you can always call functions of this object, such as .scf, to run a specific calculation. So you can also have .ph for phonons, you can have .nscf for NSF calculations, and so on. So first you call the type of calculation that you want. And here you may set any types of Quantum Espresso variables that you wish. So since this is a SCF calculation, any type of pw.x flags that you can imagine, you can also always plug here. And they are separated by the different blocks of Quantum Espresso too, such as control, electrons, K-points. You can also have cells, ions, and so on. Anything that you might define, you can define here. Once this, the type of calculation that you want to run is defined, you have 2 extra lines that you need, so it's always 3. The second one is a prepare line. So what this line does is essentially copying any file that you might need for this calculation. In the case of the NSF, of the ASF, you don't really need anything. But for a phonon calculation, we're going to be copying this SCF data to our phonon folder. So this prepare line is going to do that for us, so we don't have to do that manually. Once this prepare run is issued, you can finally run the calculation. So this is done by this function called .run, where you are able to specify the amount of cores that you want to use and also the types of parallelization that you want to use, which will depend on the code that you are using too. So these 3 lines is everything that you need to run an SCF calculation once you set the silicon object. So once you run these lines, clicking the play button on the top, he will show you just like this small fancy box telling you that the SCF is running, and you are able to check if this calculation is finished or not. So again, to remind you, I'm going to make a quick shift to Frontera. Now we are accessing Frontera from the terminal session. Everything that you're running on your MATCSSI session is being run live on Frontera. So you can actually access access this EPWPy folder, as you can see, we can go inside the notebooks basics folders that we are currently accessing in MATCSSI, and you can see that that line, that specific, these 3 lines here actually created this silicon folder here for us. So when you execute that, this created this silicon folder and this SCF folder related to this SCF calculation that we just ran. So what basically those 3 lines did is create all these folders, create our SCF input file for us. So this file is generated automatically by EPWPy based on all the properties and attributes that you defined in the code previously. And it also ran this calculation for you, where you can see the output here or just follow these calculations in real time if you need. So this is about the SCF run. So what about the band structure run, which is the next step? So if you want to run a band structure, again, you need the SCF data, for example. So you're gonna, again, define the 3 lines with your band structure general flags that you wanna use. You also will have a prepare line, which will copy the data from the SCF calculation that we just ran. And now, so finally, you're gonna run this band structure calculations with a 3rd line. So this second set of calculations, once you hit play, it's gonna generate, again, another folder, which is called band structure, BS. And here, everything has been ran. You can also see the input file that EPWPy created for the specific bands calculation. And if you have any inconsistencies here or any crashes, you can always follow these outputs to understand what's going on and coming back to the MATCSSI platform to fix it. So of course, this calculation was ran, and you can always check here that everything finished okay. So there were no crashes. So this we are currently checking directly on the cluster, but you can also check if the calculations were run directly in the notebooks we have without having to alt-tab if you want. So this is pretty much about the band structures. So this allows us basically to get the first ingredient that we need for these transport calculations, which is the electronic contribution. And we can actually plot that with some lines of Python code using matplotlib, for example, GNU-plot, or whatever you want. We have some predefined functions, such as this plot band SCF, which will make your life much easier to plot this everything without having to manually accessing the files. This will go automatically on the folder that it needs and collect the information of the file that it needs, and will produce you a plot that looks just like this. So this is the band structure of silicon, as we might expect. Here we have our indirect band gap and our X, gamma, and L high symmetry points. So this is our electronic contribution about the phonos contributions. So since we already ran the SCF, we don't have to rerun it. So we can always use again this prepare line, which will copy the data that it needs, which is the SCF calculations that we already ran. And we can also set the phonos, the phono flags that we want, and also finally run the phonos again. So everything is always 3 steps. It goes defining the type of calculation you want to run, preparing your run, and running your calculation. So your phono calculations will always also be accessible from cluster. You can go to the ph folder and you see that everything is here. So this is the ph.input file that was generated by EPWPy. And you can imagine that, like right now, we are running these calculations for a specific material, but if we wanted to run this for several materials in a high throughput fashion, for example, we could make a big loop, like a for loop, with all of this code comprised inside this for loop, and we can just change this object on the fly and run all these calculations in sequence without having to write any inputs by hand at all. So it can be very convenient. This will pretty much give us the phono contributions, and now we have almost everything that we need. We just have to run a final series of NSF calculations to collect all the block wave functions that we need. Again, 3 lines. This will generate this NSF folder, which EPW needs. You can always check the input files. And the grid for the EPW, for the NSF input file was also automatically generated by EPWPy. So you see that's explicitly written here, differently from the case of SCF, for example, where the key points are actually giving automatically, so you don't have to list all of them. This is a requirement of EPW, that's why we are doing like that. And finally, you can just check that your calculation finished properly, and it's job done, so everything is good. Yes. So with this, we have our electronic contributions, we have our phonon contributions, we have this final NSF step that we need. We can also collect the interatomic force constants in case we want to plot the phonons later on. So that's what we are doing here. We are running a quick Q2R calculation just to get the phonon dispersions as well. Once we have all of these things set up, you can go to the next step, which is pretty much starting to actually execute EPW. So similar to the other cases, we're going to have to define an EPW object as you define a SCF, for example, object for your SCF calculation. So we call our silicon object.epw, and then here we can define any EPW variable that we might need. We can always reset our material in case we also don't want to keep, let's say, those previous global variables that we define. If we don't want them anymore because we're going to run something else, we can always reset everything, and it will just give you your clean silicon object without anything that you defined after that. So you need to define this object, you need to generate the k-path that you're going to need to interpolate your band structures in your phonons, and also prepare and run again. So all of these lines are conveniently implemented for you from the construction of the EPW inputs, from the generation of the k-path that you need. It can be generated using this fillkf function right here. So once you generated this and run this thing, the first thing that you will obtain is an EPW folder that looks like this. So this is the EPW1 input file that we just generated. So everything is here, from your coarse grid, from your fine grid, and everything that's here is either set up in this specific block, or it's predefined and has like default values, so you don't have to choose them manually. So it's always nice for you to come here on these inputs and check that everything is according to what you expect, and there are no default variables being used here that you might actually maybe you don't want. So it's good to double check everything. And this calculation of EPW1, you can always check the output. And yes, so like here you can see from the beginning, EPWPy was called. It was executed in a similar fashion as Quantum Espresso. The vanillization started and finished normally. All the elements from the electron phonon matrix elements were computed, and then the calculation finishes. This is just the first step of EPW. So once this first step of EPW1 is done, where you're going to interpolate your electron phonon matrix elements, you're going to go to EPW2, where you actually run the transport. One thing that EPW1 gives us that's quite interesting is our interpolated bands. So we can actually plot both of the electronic bands that we just plotted before, and also now the phonon bands, both of them interpolated by Vannier. So you can see that these are the two outputs. This is the interpolated band structure that we got from our vannierization done with EPW. So it's the same thing that we just saw. And also the phonon dispersions, that is also another ingredient we need. We need all these frequencies and also the eigenvectors and the eigenmodes related to these phonons. So once this Vannier interpolation, first Vannier interpolation and vannierization is done, you can actually go to EPW2, where again we're going to reset a silicon object because we're going to run another EPW. So we don't want to use the options of the previous EPW run, so that's why we want to reset. And this will allow us to now define everything that we need for transport. So this is a slightly different EPW object than before, and you can see that now we are actually activating some of the transport flags, such as the iterative BTE and also carrier and so on. So anything that you might want to set for transport, you can set here. And again, you prepare and you run. This will be giving you something that looks like this. So this is a plot of mobility as a function of temperature. So this can also be extracted using predefined EPWPy libraries. So you can extract all these IBT mobilities for a given temperature or whatever you wish. And you can generate a plot that looks just like this. This is a comparison between IBT and CERTA that we just ran from that block. So you can also, of course, see the output and input from EPW2. So this is the input created by EPW2, very similar to the input of EPW1. And the output is also slightly similar on the beginning until the point that starts to actually evaluating the mobilities and the scattering rates. So first we calculate the scattering rates on this first step, and then we start to run the iterative Boltzmann transport equation, which you can follow the number of directions and so on. And the mobilities that we just plot are actually contained right here. And this is just extracted automatically by EPWPy, so you don't have to come here and collect these matrices by hand. So this will be the outputs of EPW1 and EPW2 once you run everything using these notebooks. You can also post-process some other things. You can think about plotting current as a function of field, for example, which we also have some functions that can do that, based that you extract this from the outputs of EPW. We can generate a curve like this. We can also post-process other things, such as the scattering rates, which is one of the things that we use to compute mobilities, and we can also plot them using EPWPy. So this would be the first example of transport and how you can use these Jupyter notebooks to run transport calculations with EPW. But again, we have several different examples here from polarons, from optics, and so on. Now we're going to move to another notebook where it is slightly similar. It's also an application of EPW, but here it's instead of transport, we're going to be looking into optics. So most of the things here are very similar and were already just presented on the transport section, so we don't have to pass through all of them again. But again, you can see that we always start by loading some libraries that we need, set up in some folders and some constants that we need, defining our object, and plotting some of these attributes so we can check. So different from the transport case where you are downloading the pseudo-potentials automatically, here you can see that we are actually providing a pseudo directory instead. So this is going to this folder. So this is the other option that I was mentioning. So instead of downloading them automatically, you can just point to a folder where you have all the pseudo-potentials that you might need. So in this case, what we want to do is pretty much use this quasi-degenerate perturbation theory to try to compute optical absorption with phonon-assisted processes too. So again, we have all of this first setup of quantum express of EPW, where we need to run an SCF calculation, a bands calculation. Then we can plot to check if everything is okay. We can compute our phonons that we also need in our NSF calculations in the same fashion as we did for transport. All of this is pretty much always the same, except for you're going to be using your convergent K-grids or cutoffs and so on, but like all this process is the same. And once you reach EPW, things starts to differentiate a bit. So in this first section here, we are just like interpolating the bands and the phonons as we did before. So here you can see how both of them look. And next we can actually start running the part that's more applied to optics. So here you can see that we are defining this EPW object, which is different from transport, now carries the flags dedicated to optical calculations. So for example, these three, and especially this one that activates the indirect absorption calculations. So at this stage, we are computing these things using the old methodology, let's say. We are a term like this, we are going to call them the KP method. So this is what was being implemented at the Quantum Espresso in the past in EPW in the past couple years, and what people have been using in the field, which is basically consists in evaluate these optical matrix elements S1 and S2 via the calculations of the electron photomatrix elements G, which we're getting from EPW. And once we calculate these matrix elements, we can then compute the optical absorption according to the expression on the top. So this, let's say, is the old methodology, is what we're going to use to benchmark the QDPT in this case. And by running this calculation, we can actually compute the absorption coefficient. It will look roughly like this. Of course, this is not a converged calculation, but this is just to give us a generic idea of what's happening. So if you want to instead run QDPT instead of the old methodology, most of these flags are in fact the same, as you can see, including the indirect absorption, which is now true, which is also true. But now you have this also quasi-ABS flag set to true, which activates the QDPT methodology. So in the end, both of these things should give you something sort of similar for the indirect bandgap. If you run the EPW block that we just discussed, you should be able to generate a plot that looks like, just like this. So this is exactly what I was just mentioning. You can see that the both methodologies, they actually agree quite well for the indirect regime of silicon. But once we reach the direct bandgap of silicon, the old, let's say, the KP methodology actually kind of explodes, and it does not reproduce correctly what we expect, due to the fact that we have some artificial broadening in the old methodology, while the QDPT actually reproduces exactly what we would expect from the experiment, and there's no dependency on this broadening. So that's pretty much what QDPT brings us in comparison to this old methodology here. So this is just a demonstration of how you can use these notebooks to run QDPT or the old optical absorption method. But my point is that all of these things, they are very similar. The structure are very similar. In fact, the EPW part is pretty much the same for all of them until you reach the actual EPW inputs and things starts to differentiate. The same procedure can be said for Berkeley GW if you want to run GW calculations or BSE calculations, since most of these steps are actually very similar. What the EPWPi is doing is basically facilitating your life so you don't have to set all of these inputs by hand. So this is about QDPT. We're just going to very briefly also pass by the Polaron notebook. Here, again, you can also have some information about the authors in all the notebooks. In fact, on the top, you can find some information about who wrote these notebooks. In this case, you can see that we have authors when these notebooks were changed, and the authors and when they were revised. You can find some theory to explain to you everything you're doing. And the procedure is the same as before. We start loading some modules, you can set up paths. So this is really up to you. For now, everything that we have implemented in EPW can be accessed from EPWPi. You can generate any of these calculations using EPWPi. And these notebooks are just give you an example of the different ways that you can do it. When you can either compile Quantum Espresso by yourself or use EPWPi to do it, or if you want to download pseudopotentials automatically, or if you don't, or if you want to define something automatically, or if you don't. So you can just follow these notebooks. And in the case of Polarons, we have also some very convenient functions to extract all these waves that are very important for Polaron analysis, and sometimes it can be quite annoying to actually do these plots by hand, and EPWPi just extracts all this information for you without much problems. The same thing goes for like post-processing analysis, such as convergency plots, in this case formation energy as a function of the supersized cell. So this is pretty much the three notebooks that I wanted to pass by, and also the installation notebooks. All of the other ones, they follow exactly the same procedure. So if for any type of application, from superconductivity, from the ZG method that one might be interested, you can just go to notebooks, you can follow the procedure, and then you can just start applying for your case. I think it's also very important to note that all of these Python codes and all these structures that we are presenting in these notebooks, they don't have to be used in a notebook. These are this is a Python library, and you can just actually import it in your own Python code and start using it as a normal like Python coding without actually having to open all these visualizing things. This is more an exemplification. And with this, we should be pretty much wrapping up everything that we wanted to talk about this specific introduction. So thank you very much for your attention. If you have any questions, you can always, again, access the MATCSSI website, and you should be able to find information about anything you need. So thank you very much, and till next one.